Okay, so the second set of notes are going to be more formal in terms of notation, defining what a derivative is, which is going to be slopes of tangent lines. And so you're just going to have to copy these down in your notebook, your math notebook, as I don't have printed copies of anything to fill out. So this is going to be 3.1, and we're going to talk about the first limit definition of a derivative. Saying the first limit definition of a derivative implies that there are multiple, and that is true. There are two limit definitions of a derivative. Now, before we talk about this first limit definition of a derivative, let's actually define what a derivative is. So there are three ways that we can express a derivative. And so one, we could say a derivative is a slope of a tangent line. And so that's what we started exploring in class together. We looked at slopes of secant lines. A secant line is a line that crosses through a graph at 2 points. A tangent line is a line that touches the curve or graph at just 1 point. And so a derivative is us finding the slope of that tangent line, which recall is difficult when I go to use the slope formula because I only have 1 point. Okay? A derivative is also an instantaneous rate of change. And often you will see IROC, instantaneous rate of change, to abbreviate that, okay? Average rate of change would be the change occurring over a given period of time, versus instantaneous rate of change is the change that is occurring right now in this moment, okay? And so again, secant lines, slopes of secant lines look at the average rate of change, the slope over a given interval. A derivative looks like the slope at a specific point, okay, 1 point, so instantaneous slope or instantaneous rate of change. And the third way to describe a derivative is this limit definition, okay? It's the limit of a difference quotient. And a difference quotient is basically what it sounds like. It's the division of differences, and so it's the slope formula. Right, quotient means division, difference means subtraction. So, change in y over change in x. So remember that slope formula is that change in y over change in x, or the output for x2 minus the output for x1 divided by x2 minus x1. This is a difference quotient. And so what I explained in the video you should have watched prior to this is that I'm looking at the slope of secant lines as one x value moves closer and closer to the point of tangency, okay, the point on the tangent line. And that movement of closer and closer is that limit piece of things, okay? So just to review what I went through on the Desmos exploration is that if I have a secant line through, and we'll say the point A, comma, f of A, and we'll say x, comma, f of x, right? This is my, this is like my x sub 1 and my my y sub 1. And this would be my x sub 2 and my y sub 2, okay? Then define the slope of the secant line, or that average rate of change. okay, slope of secant line, okay, I would say that that slope is equal to f of x minus f of a, right, change in y, divided by x minus a. That would be the slope of my secant line, or the average rate of change. The slope over a given interval where I know two x values associated with 2 points, okay? And again, this would be like saying change in y over change in x, okay, delta y over delta x. So again, to find the slope of the tangent line, right, where I'm only given 1 point, given one x value, or 1 point of tangency, okay, I'm going to have to pick values of x that get closer and closer to that point of tangency, the point on my tangent line and my curve, okay? And I'm going to evaluate the slope with that point of tangency and each of those new x values, or the points associated with those new x values, okay? And the big idea here is that the smaller the interval between those x's, so the closer those x values are, the better the secant line, or the better the slope of the secant line, will estimate the slope of the tangent line. And again, if you go back to that Desmos video, if you need to watch it again, that's the idea of the fact that I'm picking x values either on the right side or the left side of that point of tangency. And I move those x values closer and closer to that point of tangency. If I find the slope of the secant line using those 2 points, the closer my x is to the given x value, the point of tangency, the more accurate the slope of the tangent line will be. And mathematically speaking, we say that this is the limit as my x values get really close to that a value, that point of tangency, okay, of the slope formula. Change in y over the change in x. And all of this represents the derivative. This is the third representation of a derivative. So when I come back up here and say the limit of a difference quotient, that's what I'm writing. The limit as x approaches a, okay? Remember, for this secant line, we have this a f of a. This a f of a would be my point of tangency, or the point that's on the actual tangent line. And the x f of x is the point that's moving, okay? The x values are moving closer and closer to the given point of tangency, okay? what this is this is being used to find a derivative. And we indicate we're finding a derivative by using this notation, f prime of a, okay? So this notation says find the slope of the tangent line drawn to f of x at x equals a. That's what that notation says. This f prime, okay, this prime is this notation right here. Looks like an apostrophe, okay? So this is written as f prime of a. And that says find the slope of the tangent line drawn to f of x at x equals a. And when we say slope of the tangent line, what we're saying is find the derivative. A slope of a tangent line is the derivative, okay? So when I say find f prime of a, I'm saying find the slope of the tangent line, which is a derivative, okay? And in order to find the slope of that tangent line, I need to employ this limit of the slope of my secant line. And we'll practice more with that as we move on. All right. Hopefully you took some good notes, and I will see you in class tomorrow.